Now, what I'm planning to do about scattering is probably we will be spending this week and part of next week. Okay, I will first discuss the one-dimensional Dirac delta potential. Now, we will especially see that in this case, the forward scattering is non-zero.
One-dimensional scattering is like...
Yeah, it's either tunneled or scattered. Then we will have, this is one example we will study, then the finite potential well. And the spherical shell. Now in this finite potential well, we will assume that the V as a function of R is equal to V0, which is less than 0 if R is less than A, and 0 if R is larger than A. So it's kind of a potential well, a spherical potential well close to the origin. Now you should already know that this problem has bound states. Now we will see how the bound states affect the scattering. Also in the first problem in the Dirac delta potential, if the overall coefficient is negative, if it's an attractive Dirac delta potential, have you solved that problem? It has a one bound state, just one. And thirdly, the spherical shell will be the V of R. It will be lambda times Dirac delta R minus A. So it's just a shell. No potential inside, no potential outside. And what happens here, I mean, if you just think of it classically, it's like you have a spherical ball. If you put something inside, it will stay there. If you put something outside, it will stay there. It will not be able to penetrate. In the quantum theory, it corresponds to taking lambda to be infinite. If lambda is infinite, then whatever you put inside, so it will just stay there. So you have bound states, effectively. So states that are bounded in space. They don't extend until infinity. But of course, if lambda is not infinite but a finite value, you would expect these states to tunnel through your potential, so they will leak out. So even if you create a state in that inside your potential, they will leak out. They will not be eigenstates. Nevertheless, they will be living a long time if lambda is large enough. So those are what we call the resonances. So there will be resonances inside this potential, and we will also see how these resonances affect the scattering potential, the scattering process. Now, the easiest one will be the Dirac delta potential. Now, the Dirac delta potential, let's first solve it, find the bound state using just ordinary quantum mechanics. We will assume that, example, V of x is equal to lambda times Dirac delta x. So we have this Dirac delta potential at x is equal to 0. And we will assume that lambda is less than 0 to be able to find the bound states. And the Schrödinger equation we need to solve is this one, h bar squared over 2m v squared psi by dx squared plus lambda Dirac delta of x psi. This is equal to e of psi. Now this problem has a mirror symmetry if you just send x to minus x, so it's still, you have exactly the same equation. So the solutions should be either even or odd. But even solutions do not, I mean, you cannot have even odd solutions because odd solutions would vanish at x equal to 0, and hence they will not see the Dirac delta potential. So you only have the even potential, even solutions. And the even solutions, let's just define E to be minus h bar squared kappa over 2m. So the solution will be just psi is equal to e to power minus kappa times the absolute value of x with some normalization. So this is the general solution you have. What you do is you just solve the equation for x not equal to 0. So it's just the second derivative is equal to kappa squared. Kappa squared times the wave function itself. And so this is the solution you have. And being the normalization condition. Well, this is the only normalizable solution. You also have non-normalizable solutions, but in quantum mechanics, in bound states, we only want the normalizable ones. And then we have to determine what are the possible values of kappa. Not all values of kappa will be allowed. And to determine the possible values of kappa, what we do is you just take the integral of your differential equation, minus h bar squared over 2m d by dx psi prime plus lambda Dirac delta of x psi dx. This should be equal to e times psi dx. And you integrate over x from 0 minus to 0 plus. Just from the left of this Dirac delta to the right of Dirac delta. And keep in mind that the wave function has to be continuous. Its derivative need not be continuous, but the wave function should be continuous so that we can take its derivatives. So if you just take this derivative, the integral, okay, so the first term is nothing but the integral of total derivative. It's kind of trivial, minus h bar squared over 2m, psi prime evaluated at 0 plus, minus psi prime evaluated at 0 minus. The second term just gives lambda psi evaluated at 0. And the right-hand side, since psi is a continuous function and a finite function, we don't want the wave function to be divergent, so you are just integrating a finite function over an interval that has 0 length, so that's just 0. Now if you just take this psi prime at 0 plus, this is nothing but the derivative with respect to x of n e to the power minus kx evaluated at x is equal to 0 plus. We are looking at the positive values of x, so absolute value of x is just x. So this is equal to minus n times kappa at x is equal to 0. If you do the same thing for 0 minus, n times e to the power minus kappa minus x this time, since you are evaluating x at the negative values of x, absolute value of x is minus x is equal to 0 minus, this is equal to n times kappa. So if you just put it in the above equation, we get minus h bar squared over 2m multiplied with this psi prime at 0 plus is minus n times kappa, and psi prime at 0 minus is n times kappa plus lambda psi 0. This is equal to 0. Now psi 0 is just n. So I can just cancel the n's, and we get h bar squared over m times kappa plus lambda is equal to 0, or kappa should be equal to minus lambda times m over h bar squared, which should be positive, by the way. So we have a bound state only if lambda is negative. Otherwise we don't have a bound state. So we have the wave function. I will not put the normalization. Some normalization, e to the power minus lambda, absolute value of lambda, m over h bar squared, absolute value of x. This is our wave function. And the energy is minus h bar squared over 2m times kappa squared, which is lambda squared m squared over h bar to the 4. Minus lambda squared over 2 h bar squared. So basically if lambda is negative, this is your x. So here is x is equal to 0. You have your Dirac delta. And the wave function you have, it just decays up to infinity. There is no place where it oscillates. So this is how your wave function looks like. Now let's look at let's review this problem. Okay, this is for the negative energies. For positive energy states, we can also do something similar. But let's use the equation we had derived on Friday, I think. If you remember, we had this general solution, psi of x. This is equal to psi 0 of x plus integral from minus infinity to infinity g of x minus x prime v of x prime psi of x prime. Now, in this special case, we will be able to solve this equation. So g, and if you remember, g in this case should satisfy minus h bar squared over 2m del squared minus e. G should be equal to Dirac delta x minus x prime. So if G satisfies this one, then the above equation is a solution of our differential equation. Where, of course, psi 0 is again the solution of the homogeneous equation. And no, we are done. We will be done. Now, I will not go into the details of calculations of G. It's just similar to what we had done in the three-dimensional case. The only difference will be here we won't have, we will go to the Fourier space, then you will solve the equation in Fourier space and transform back to the real space. Of course, here we won't have these angular integrations, but nevertheless, if you remember, after the angular integrations, we had this integral from minus infinity to plus infinity. Here it's already from minus infinity to plus infinity, so nothing to worry about. Now, if you just put this, if you just solve it, this is what you obtain. Psi of x should be equal to psi 0 of x minus 2 pi I m over k from minus infinity to plus infinity e to power I k x minus x prime over k psi of x prime v of x prime. This is the equation we have. Now, oh sorry, this k doesn't exist. Okay, in this one-dimensional case, we don't have, if you remember, in the three-dimensional case, the outgoing plane wave was e to power I kr over r. In this one, we don't have this 1 over r dependence, basically because in one dimension, the reflected wave does not spread. So it's just one-dimensional motion. That 1 over r was due to the spreading of the wave function. Now, we know that v of x prime is equal to lambda Dirac delta of x prime. So we can just evaluate that x prime integral, and that gives you psi of x is equal to psi 0 of x minus 2 pi I m over k minus infinity to infinity. There's no integral. E to the power I kx times psi at x is equal to 0 lambda. Well, we can do one more thing. I can just set x is equal to 0 everywhere. So psi 0 is equal to psi 0 evaluated at 0 minus 2 pi I m lambda over k times psi 0. And I can solve for psi 0. My wave function at 0 separation is equal to 1 over 1 plus 2 pi I m lambda over k times this one. So basically, I know my psi of x. So psi of x is just psi 0 of x minus 2 pi I m lambda over k e to the power I k x 1 over 1 plus 2 pi I m lambda over k times psi 0 at 0. And I can even do one more step. I can just set psi 0, 0 to be 1. So you see, if you remember psi of x from our scattering theory, psi of x should be equal to e to power I kx plus some f e to the power I k absolute value of x. If you just repeat the argument in the one-dimensional case, so the first one is the incoming wave. There is a scattering source, and from the scattering source, some of it will be scattered backward, some of it will be scattered forward. It is this one, this plane wave leaving from my Dirac delta, and f squared just gives us the total scattering cross-section, differential cross-section. Now, one thing is, if you just compare this general expression and this scattering state solution, well, f, whether it is scattered in the forward direction or in the backward direction, it's the same. And f is given by 2 pi I m lambda over k. Now let's also multiply this k plus 2 pi I m lambda. Now, if you remember, we were saying that we had this hard sphere scattering. And for some reason, we found more particles were being scattered than we would classically expect. So, and we were saying that there are also particles scattered into the shadow region of this sphere. So basically, we have an explicit example over here. We have this. The shadow region is just behind the potential, and there are particles scattered behind the potential. Now let's look at one thing. Now we know, we said that we are looking at positive energy solutions, but we never used the fact that we are looking at the positive energy solutions really. So we always said that K should be positive, but we never really used it. In fact, energy can be negative, no problem. If energy can be negative, then K will be negative. K will be imaginary. And if we set K is equal to, let's say, I times kappa, so if energy is negative, that if there is a solution with negative energy, then rather than that, let's look at this possibility. Let's look at this F. F diverges when K is equal to minus 2 pi I m lambda. Now, what happens when F diverges? Well, psi of x is equal to e to power I kx. I didn't substitute it yet, this value. Well, we can just substitute it. 2 pi m lambda of x, or rather than that, let me just use psi 0. Of x, because I would later on generalize it to 3 dimensions. Plus f, which diverges, but let's just keep it there. E to the power 2 pi m lambda x. And of course, we have to normalize this properly. But if we normalize this properly, the second one, f, is divergent. So it's basically just ignore the first one. It's finite. And then this would be proportional to, once normalized, e to the power 2 pi m lambda x. Well, I probably have an extra factor of 2 pi over here. Let's look at this solution. I have to insert some h bars. Compare it with this one. As I said, I have to insert some h bars. I shouldn't have this 2 pi over here. I mean, if you do it properly with proper normalizations, this 2 pi is not there. Well, I have my bound state equation with the bound state energy. E should be equal to, h bar is 1, so k squared over 2m. That is, well, this is my k. If I take it squared, that is m lambda squared over 2. So for some reason, I started with a scattering problem. I obtained my scattering cross-section. And then I saw that I have a pole in my scattering cross-section for an imaginary value of my wave vector. And it just turned out to be equal to my bound state wave vector. Now, this is not a coincidence. You see, if you follow our treatment, what we had done was we said that, okay, psi of x should be equal to the solution of the homogeneous equation plus the scattered wave, which is, we said that at long distances, f, which depends on k and also on where we are, e to the power I kr over r. So this should be how my wave function should look like in 3 dimensions also. I mean, this argument is whether you are in 3 dimension or 1 dimension, it doesn't change. So this should be how my wave function should look like at a point sufficiently far away from my potential. So there is an incoming wave, if there is an incoming wave, and there is a scattered solution. But if you think of the bound states, in the bound states there is no incoming wave, and at infinity they should decay as exponentially. So if we say k is equal to I times kappa for kappa positive, then the second solution is exponentially decaying, just like our bound states. It has exactly the same functional dependence. But the only problem is that the first term, the psi 0, should also go to 0. One way of making sure that the first term is not there is that f evaluated at I kappa should diverge. So the second condition basically tells me that f should have a pole when I have a bound state. So that is another way of solving for the bound state. That you look for the scattering amplitude for an arbitrary energy or arbitrary wave vector. You just analytically continue it to imaginary wave vectors. If there is a pole there, that is your bound state. It will be there all the time. So basically, in the other 2 examples that we will study, we will start on Friday. That is what we will be trying to do. We will try to calculate the scattering amplitude for an arbitrary k and look for the poles. In the first one, we will see that, I mean, if V0 is very small, then there will be no poles. As V0 gets larger, we will start finding 1, 2, or many poles depending on the value of V0. Now the second example will be more interesting because V0 will, when we calculate the scattering amplitude, it will not have poles in the real axis. That is, when we assume that K is just pure imaginary, or energy is real and negative, we will see that it doesn't have any poles. But when we assume that energy is imaginary, I'm not talking about the K, I'm talking the energy. When energy is imaginary, then the third problem will have poles. And we will just interpret those poles in complex energy as these resonances. So remember what we said was, okay, if you put a state inside this shell, the ball will prevent it to leak out immediately. It will stay in the ball for a long time. But if you just say, let's say, if you just imagine you put many particles inside your shell, their number, which is proportional to wave function squared, and we had this argument before, their number will be decreasing with time because some of them will be tunneling out of our shell. But this basically means that psi is a function of t, the time. It will be e to power I et, this is the oscillation in time, minus gamma over 2t. But this is nothing but an imaginary energy. I times E plus I gamma over 2t. So we will have poles at imaginary energies, and the real part will be the average energy. The imaginary part will be just the width, or the inverse imaginary part will be the lifetime of that state. So that we will do in details. Now, any questions up to here? Now in our remaining time, let me just give some terminology. Now, if you remember, we had these phase shifts. We had seen that if we just assume spherical waves of a definite angular momentum going towards our potential, when they come out, they will be against spherical waves of the same angular momentum. The only possibility is a phase shift. So this is called the S matrix element. For the time being, it's just a terminology. So whenever you hear S matrix, just remember this one. Well, it's the matrix element of it's actually what this S matrix is. Suppose you have your initial state. Well, we are not doing the time-dependent part over here. You have the initial state. And of course, it will evolve in time. So you create an initial state, so it will evolve from the initial time to the final time. And you are looking for the possibility that it will make a transition to the final state. So this evolution matrix is what we call the S matrix. And this is a matrix element in the angular momentum basis. It is unitary. Time evolution in quantum mechanics is unitary. Well, if a matrix is unitary, then when you diagonalize it, the eigenvalues should have unit norm. Well, the unit norm is e to the power 2i delta L, the phase shifts for a given L. Now, we will also define a T matrix, 1 plus IT. This is called the T matrix. It's basically, 1 is no scattering, T is the scattering. T describes the scattering process. Now, we had this so-called Lippmann-Schwinger equation. This is equal to psi 0 plus. Now, did we discuss this one? No, let's write it from the beginning. So this is what we are trying to solve. H plus V acting on psi, this is equal to E psi. And what we do is we just H0 plus V. We say H0 minus E psi should be equal to minus V psi. Or psi, we can write it as psi 0 plus V over E minus H0 psi. And psi 0 is the solution of this one. Is V equal to 0 solution. Let me also pay a bit more attention because V need not commute with 1 over E minus H0. So we take the state psi, act with V first, and then multiply with 1 over E minus H0. And what we call G, or R prime, was basically R 1 over E minus H0 R prime. Now we usually if you look at this equation, okay, we don't know psi, this kind of, it corresponds to our integral equation. And the solution we are looking for, psi, appears on both on the left-hand side and on the right-hand side. So we would rather express the right-hand side in terms of only of psi 0. So we can define V psi as t times psi 0. This is the definition. If V is 0, then t is 0. We're just defining this operator t. We didn't yet show that S is equal to 1 plus IT. We didn't show that yet. But what we are saying is we just define this t. So in terms of this t, psi is equal to psi 0 plus 1 over E minus H0 V t times psi 0. So now, okay, we didn't really gain much at this step because we know psi 0, but this time we don't know what t is yet. But we can solve for t. And in order to solve for t, what we need to do is just multiply both the left-hand side and the right-hand side by v. So we get v psi is equal to v psi 0 plus v times 1 over E minus H0 t times psi 0. But the left-hand side is now t times psi 0. And whatever t is, it should hold for all possible values of psi 0. But psi 0 is an eigenstate of H0, so they form a complete set. So any state I can write in terms of psi 0s. So that basically tells me that t should satisfy this equation. T should be equal to v plus v times 1 over E minus H0 times t. Well, we can solve for t from this equation. T minus v 1 over E minus H0 times t should be equal to v. Or 1 minus v 1 over E minus H0 t should be equal to v. Or E minus H0 minus v times 1 over E minus H0 t should be equal to v. Well, this is E minus H multiplied with 1 over E minus H0. T should be equal to V. So we basically have T is equal to, let's see, V 1 over E minus H, E minus H0. This is our t. Well, at this point, it's also not so useful. But at least one thing you can see from here, if there are bound states, then t has a pole in the bound states. You see, if H has an eigenstate that is negative, then H minus E will be singular for negative E. That is, it will diverge for that state, 1 over E minus H. Now, for positive energies, you don't have that singularity, by the way. Although H has positive eigenvalues, so does H0. So H0 minus E divided by H minus E is not singular at positive energy eigenvalues, but it is singular at negative energy eigenvalues of H. Do you agree, disagree? Yes. The poles cancel for positive eigenvalues, but H0 doesn't have any negative energy eigenvalue. So it doesn't cancel. Now let's calculate this T for our, let's say, for our Dirac delta potential. Well, it will be easier to go back to this expression over here. This one. Solve equation. And let's try to calculate this matrix element. This should be equal to V, the matrix element of V, plus x prime V 1 over E minus H0 T x. This is equal to, well, the potential is just lambda times Dirac delta x. The remaining matrix element just gives me Dirac delta x minus x prime, plus lambda times Dirac delta x prime 1 over E minus H0 Tx. Well, the first line I can just write as Dirac delta x times Dirac delta x prime plus lambda Dirac delta x prime 1 over E minus H0 T of x. Or let's also write it in another form, x prime plus lambda Dirac delta x prime integral over x double prime, x prime 1 over E minus H0 x double prime T of x. So this is x prime T x. Well, you see both of the terms on the right hand side, they are proportional to Dirac delta x prime. So it just tells me that whatever this matrix element is, I don't yet know its exact form, but it should be proportional to Dirac x prime times some function that depends on x only. You see the first term, if you factor out Dirac delta x prime, the remaining only depends on x. If you look at the second term, well, it doesn't. Dirac delta x prime is already factored out, and well, what remains, wherever you have x prime. Sorry, there I made a mistake, or no. Okay, that x prime is just 0. Basically, I can put 0 everywhere, and the second integral only depends on x and nothing else. So whatever the x value of t is in that integral. Now, if this is true, then we can just put this expression into the above equality, and we get f of x should be equal to lambda times Dirac delta x plus lambda times, well, you see this matrix element over here then is just Dirac delta x double prime times f of x. Because the matrix element is Dirac delta. We already know that this matrix element contains a Dirac delta in the bra, in the argument of the bra. So that's what I use in that integral. Then I can just evaluate that integral. So Dirac delta x prime, well, x prime is 0, 1 over a minus h0. Using that, integrating over x double prime, that is also 0, times f of x. Sorry, this is... Now this Dirac delta x prime we had already factored out. This is f of x, okay. Yeah. Now I can find what f of x is equal to lambda Dirac delta of x divided by 1 minus lambda 0, 0. Or Tx is equal to lambda Dirac delta of x Dirac delta of x prime divided by 1 minus lambda 0, 1 over e minus h0, 0. This is our T matrix in coordinate space. Well, if you evaluate it in momentum space and find where its pole is, that is where your bound state is. Any questions? Well, you see, going to the momentum space is not that complicated. If you just go to the momentum space, P prime, let's say, this will be just lambda Dirac delta P minus P prime. The denominator is just a constant. It's meant nothing but your Green's function is at 0. And in fact, this part is what we had obtained as our f. Any questions?
How can we interpret complex energy?
We will do it. I mean, basically, this is our interpretation. Now, we are not saying complex energy. What we are saying is that it has poles on the complex plane. We will be evaluating these T matrix elements, and we will see that the T matrix elements have poles. Now, in the previous example, in the Dirac delta example, now this is basically your T matrix element. Now, the T matrix element had poles when the energy was negative. Now we will see in this third example, when we study it in more detail, we will see that, and this poles in the negative energy, we interpreted them as our bound states. Now, this third example, the spherical shell potential, we will see that we will first solve the case when lambda is infinite, so that we already know where the bound states are. Then we will show that we will calculate the scattering matrix element, T matrix elements, and show that they have poles, not on the real line, not for real values of energy. They have poles for imaginary values of energy. And we will also show explicitly that imaginary value, real part of that imaginary value of the energy corresponds to the energies, at least they will be shifted slightly, but they will correspond to the bound state energies when lambda is infinite. Now we will say that when lambda is finite, basically we have what's called resonances. They are not eigenstates. They are decaying states. But they are very close to, if you set lambda to infinity, the resonances will be very close to the energy eigenstates of the lambda infinite energy states, stationary states. But if lambda is not infinite, we know that they will be decaying. We will see that the imaginary part, we just interpret it as the lifetime, well, the inverse lifetime. So that's basically how, when you look, if you ever look at any particle physics expert book or any new particle discovery, since we are doing experiments in real energies, if there is a pole in the complex energy plane, we cannot see that divergence. But what we see is, just imagine like this. This is the real axis. This is the imaginary. At this point, there is a pole. If you are going along this line, that is, if you are not going through the peak of the mountain, but a bit shifted, you will see a hill. So that is what we observe in experiments.
That means it's a bound state, and the bound state is a
we interpret these as resonances. They live long enough to be identified as almost a bound state, but they still have a finite lifetime. So then we say that, okay, this is the mass of the resonance, and this is the width of our resonance. Well, except then the electrons and neutrinos and the proton and neutron, whenever we say that, oh, we have a particle, this is basically what we mean. For most of them, they lived long enough so that we can see their trajectory also. So in those cases, there's no problem with identifying as a particle. But there are also those cases when they live very short and their speeds are slow, so they cannot travel a long distance, so we cannot see the trail. But nevertheless, we see their signature in the final states. And after this, in the last few weeks, we will be discussing the path integral. And that will be the end of the semester.
But the potential is not some finite
You mean such a potential, V of R? This one? Well, once the potential goes to infinity, you cannot penetrate that. So they are bound states. They are stationary states. So whatever you put inside, it will stay inside. Whatever you put outside, you will stay outside. Now, the complication arises when it's not infinite, but finite. In this case, if it is high enough, whatever you put inside, it will stay there for a long time. So it's almost a stationary state, but not exactly, because there will be a finite probability of tunneling. So basically, these particles we identify with states, with the poles in the complex energy plane, not on the real axis. I think it's Feynman. It's Feynman's path integral. But other people had similar ideas that led Feynman to its development of the path integral. Okay, so see you on Friday.